Good afternoon, everyone. My name is Rui Yao, and I'm from Fudan University. I'm glad to share our paper entitled BMW Tree today. It's about implementing a large-scale, high-throughput, and modular programmable packet scheduler. This is a joint work with the Pongcheng Laboratory and New York University. Packets from different flows will contend for the output link. The flow scheduler will decide which packet to transfer. A lot of packet scheduling algorithms have been designed for different application goals. However, few of these algorithms are put into use on chips due to high hardware cost. It's indispensable to build a programmable packet scheduler to enable them. PIFO is a popular model in recent years to realize programmable packet scheduling. In the PIFO model, each packet is tagged with a rank by the rank function. Different packet scheduling algorithms can be implemented by changing the rank function. The head packets of non-empty flows are stored in a priority queue with ascending ranks. The packet with the smallest rank goes first. Modern data center networks demand low time and space complexity on programmable schedulers. For one thing, the number of flows in the data center is growing explosively thanks to virtualization. Programmable schedulers are expected to be scalable enough to isolate and pace an enormous number of flows. For another thing, with increasing link speeds, the time budget to make scheduling decisions is also getting smaller, and time-sensitive applications require nanosecond-level precision. So, programmable schedulers are expected to have high throughput. In short, modern networks need a large-scale and high-throughput programmable packet scheduler. There are many hardware designs for the programmable scheduler. Heap-based implementation utilizes SRAM to store nodes and has a large scale. However, T-heap has vested idle cycles, and pipeline heap features expensive hardware designs. Register-only implementation has a high throughput, but it suffers from small scale, which can support no more than several thousand flows. FIFO-based approximation employs FIFOs to implement PIFO, which sacrifices accuracy in exchange for large scale and high throughput. None of them combine accuracy, large scale, and high throughput. We propose BMW Tree, balanced multi-way sorting tree, to implement an accurate, large scale, and high throughput programmable scheduler. Our work consists of one data structure as well as two hardware designs. First, I will show the data structure. Each node contains up to m unsorted elements in an m-order BMW tree, and the heap property is satisfied. Each element represents a packet and carries the packet rank, value, and the counter. We show a 4-order BMW tree with 2 levels here. Subtrees are distinguished by different colors. The counter records the number of elements in the subtree. Now, let's see the push operation. Elements are always inserted into the leftmost least loaded subtree, supposing that there is a push 17 operation. The fourth subtree is chosen and the counter is incremented by 1. 17 kicks 29 down to the second level to satisfy the heap property. On the second level, the second subtree is chosen. 29 finds an empty slot in it and occupies it. The counter is increased by 1 and the push operation finishes. For the pop operation, BMW tree always pops the smallest value in the root node and the counter is decremented by 1. 10 is the smallest, so it's popped out. To satisfy the heap property, the smallest element in the subtree is lifted from the second level to fill the vacant position. The heap property is satisfied and the pop operation finishes. BMW tree has the following properties. It is modularized. Modularization simplifies the deployment and upgrade. It has insertion balance, which means each insertion can make the tree more balanced. With a balanced structure, BMW tree consumes less power. BMW tree is also pipeline friendly, with autonomous nodes. Operations on each node of the tree are independent of the rest of the subtree. Thanks to these properties, hardware frequency is independent of the tree depth in theory. One of the hardware designs is based on registers. We call it RBMW for short. RBMW is modularized, and each node connects the parent and children only, greatly reducing the hardware complexity. The details of the modular node can be found in the paper. With the pipeline, the RBMW can deal with consecutive push and pop every 2 cycles. Despite its high throughput, RBMW's capacity is limited by the register resources. To reduce register usage, we propose ranking processing unit-driven BMW tree, RPU-BMW for short. Since BMW tree is modular and each node is autonomous, we design a ranking processing unit to complete the computing tasks of each node. We store nodes of each level in an SRAM. Nodes in SRAM will be dynamically loaded into or off from RPU and time share the RPU. For the push 70 operation, Node 1 and Node 5 are operated by RPU in turn. Now, the design achieves large scale, but the throughput is low. During the pipeline process, there is only one active node in each level at any time. To improve the system throughput, we can set one RPU for each level of the BMW tree, and each RPU will be shared by nodes on the same level. The root node exclusively occupies the first RPU. In the lower levels, only the nodes accessed by the current push or pop operations are placed in the corresponding level RPUs. When RPU completes the operation, the node will be written back to SRAM. Data from different levels interact through the RPU array. Multiple RPUs run in the pipeline. We show how push and pop are processed on the 2-level RPU BMW here. More details can be found in the paper. RPU BMW is also modularized. The ranking processing unit only connects to its predecessor and successor. The details of RPU can be found in the paper. With the pipeline, the RPU BMW can deal with consecutive push and pop every 3 cycles. As the capacity of BMW tree grows exponentially, only a few RPUs are needed for large scale. RPU BMW achieves both large scale and high throughput. The prototype of RBMW and RPU BMW is written in Verilog and implemented on XCU200 FPGA. We also synthesize RPU BMW in GlobalFoundries 28 nanometer process. The result shows the frequency and the resource consumption. It shows that RBMW can support as many as 5,000 flows. With the same capacity, the 2-order BMW's throughput is 4.8 times that of PIFO. RPU BMW can scale to 87,000 flows, much larger than PIFO. With a similar capacity, the frequency of RPU BMW can be up to 5 times that of PIFO. The frequency of RPU BMW can be as fast as 600 MHz, reaching a scheduling rate of 200 million packets per second. RPU BMW supporting 37,000 flows has an even smaller area than a 1,000 PIFO. To conclude, we propose a novel data structure balanced multi-way sorting tree and build 2 hardware designs based on it, RBMW and RPU BMW. RPU BMW is the first accurate PIFO implementation supporting over 18,000 flows at as fast as 200 million packets per second. Thank you. I'm happy to take any questions.